Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 18, looking more carefully at parallel lines. So this is a classwork for a classroom setting. I'm not going to do it, but I will read it. It says, opening exercise, exchange problem sets from Lesson 17 with a classmate. Solve the problems posed by your classmate while he or she solves yours. Compare your solutions and then discuss and resolve any discrepancies. Why were you asked only to locate the point of rotation rather than to rotate a pre-image to obtain the image? And how did you use perpendicular bisectors in constructing your solutions? So this would be a classroom setting and their answers will vary, so I'm just going to leave that to you. Okay, so here's the discussion. It says we say that two lines are parallel if they lie in the same plane and do not intersect. Two segment arrays are parallel if the lines containing them are parallel. Okay. Why is the phrase in the plane critical to the definition of parallel lines? Explain and illustrate your reasoning. So I brought this picture in from the internet, and these streams that come out of airplanes because of the moisture in the exhaust and the atmospheric temperature, I believe, is what causes them to either be visible or invisible. This here shows a really busy area for air travel. And let's just look at, let's say, I thought I'd already chosen this, but anyhow, let's say this jet stream right here, or contrail. It looks like it intersected this one, or even this one here. But these are all on different levels, elevations. So if these two planes were at this location at the same time, yes, they would crash if they were on the same plane. But if one was below the other, which it's hard to tell, so if I move this down, it still looks like they crossed somewhere. That is what is defined as a skew line. So the reason that we have to say in the plane, obviously these two lines are not parallel, even though they don't intersect because they are on different planes. That's what they're saying. Okay, so two lines in three-dimensional space are called skew lines if they do not lie in the same plane. In this case, they do not intersect because if they did, they would share a plane together and are not parallel. If they were parallel, then they would both have to lie in the same plane. In Lesson 7, we recalled some basic facts learned in earlier grades about pairs of lines and angles created by a transversal in those lines, to those lines. One of those basic facts is the following. Suppose a transversal intersects a pair of lines. The lines are parallel if and only if a pair of alternate interior angles are equal in measure. So our goal in this lesson is to prove this theorem using basic rigid motions, geometry assumptions, and geometry assumption we introduced in this lesson called the parallel postulate. Of all the geometry assumptions we have given so far, the parallel postulate gets a special name because of the special role it played in the history of mathematics. Euclid included a version of the parallel postulate in his books, and for 2,000 years people tried to show that it was not a necessary assumption. Not only did it turn out that the assumption was necessary for Euclidean geometry, but study of the parallel postulate led to the creation of non-Euclidean geometry. So non-Euclidean geometry is, think of it as spherical geometry, geometry not on a flat plane. Okay, so page 2 brings us to the basic fact above. Really has two parts, which we prove separately. So number 1 is, suppose a transversal intersects a pair of lines. If two alternate interior angles are equal in measure, then the pair of lines are parallel. 2 says, suppose a transversal intersects a pair of lines. If the lines are parallel, then the pair of alternate interior angles are equal in measure. Okay, so that's just the converse of number 1. The second part turns out to be an equivalent form of the parallel postulate. To build up to the theorem, first we need to do a construction. So example 2 says, given a line L right here, and a point P not on that line. Follow the steps below to rotate L by 180 degrees to a line L prime that passes through P. So we want a perpendicular, not bisector, because that would be cutting it in half, and you can't cut a line in half because it goes on forever and ever. You don't know where the midpoint is. So this is a perpendicular line of intersection. A says label any point A on line L. So let me get my pen and let me put a dot right here, and I'll call that A. B says find the midpoint of segment AP using a ruler. Okay, so it says measure the segment of AP and locate the point that is a distance AP divided by 2 from A between A and P. All they're basically saying there is get a ruler. Okay, and measure it. I prefer the metric system over fractions any day. So if I put that right there and rotate it to P, that is 25, 6, 7, 8, 28 millimeters. So half of 28 is 14. So it says find the midpoint of AP and label the midpoint C. So I'll put the point at 14. Here's 10, 11, 12, 13, 14 would be right here. Move my ruler, and I'm going to call that midpoint C. Let me do a better C. That's midpoint C. Perform a 180 degrees rotation around center C to quickly find the image of L under this rotation by hand. Okay. So what we're going to do is part 1 says to pick another point B on line L. So let me switch to green for this. Pick another point B. So I'll about maybe like right here and call it B. Step 1 done. Draw a line CB. Okay, there's line CB. Draw a circle, center C, radius CB. So now I need my compass. Center at C means to put the point of the compass at C. Try to do this as accurately as possible. Right there. Radius of CB. Like so. Okay, so that's this. Label the other point where the circle intersects line CB by Q. That's right over here. So that's Q. Draw PQ. So then I take my ruler and draw a line through P and Q like so. Oops, it's supposed to be blue. And there is line PQ. All right, so D says label the image of rotation by 180 degrees of L by L prime, which equals a rotation around C 180 degrees line L. So basically what we have done is we've taken this line L, rotated it 180 degrees around this point, and so if A were here, A prime would be over here. If B's here, B prime would be over here somewhere. So this line here needs to be labeled the rotation centered at C, comma means the number of degrees, comma the degrees, and what you rotated, and that was line L. So a rotation centered at C, 180 degrees, line L. Now we answer some questions. How does your construction relate to the geometry assumptions stated above to rotations? Complete the statement below to clarify your observations. R, centered at C, rotation about C 180 degrees is a 180 degree rotation around C. Rotations preserve lines. We rotated a line, so they preserve them. Therefore, the rotation centered at C 180 degrees maps the line L to the line L prime. That's our image, L prime. What is the rotation C a 180 degrees A? What point rotated 180 degrees? What did this point become when we rotated line L 180 degrees? And the answer to that is point P. Okay, page 3 brings us to example 3. The line L and L prime in the construction certainly look parallel, but we do not have to rely on looks. Claim. In the conclusion, L is parallel to L prime. We're just claiming it. In the construction, I say conclusion. In the construction, L is parallel to L prime. That's what we're claiming. We need to prove that. So the proof says, we show that assuming they are not parallel leads to a contradiction. So this is a proof by contradiction. If they are not parallel, then they must intersect somewhere. Call that point X. Since X is on L prime, it must be the image of some point S on L under the rotation around C 180 degrees, i.e. R sub C 180 S equals X. So you rotate the point S that's on L 180 degrees around that point C that we just did, and we find the point X on L prime. Since the rotation about C 180 degrees is a 180 degree rotation, S and X must be the endpoints of a diameter of a circle that has center C. In particular, line SX must contain C. Since S is a point on L and X is a different point on L, it was the intersection of both lines. We have that line L equals line SX because there's only one line through 2 points. But line SX also contains C, which means that L contains C. However, C was constructed so that it was not on L. This is absurd. There are only 2 possibilities for any 2 distinct lines, L and L prime in a plane. Either the lines are parallel or they are not parallel. Since assuming the lines were not parallel led to a false conclusion. The only possibility left is that L and L prime were parallel to begin with. Okay, so just reading that, it may just seem a bunch of total confusion and you still don't know what they were saying. So let me try to explain what happened here. Alright, so we showed that assuming they are not parallel leads to a contradiction. If they're not parallel, then they must intersect somewhere. Call that point X, since X is on L prime. So if I had line L like so, and let me name it L, and then I have another line, say here, and I'm going to call that X, or SX. So if this is a point S, and this is a point X, all right? So what's it say here? Call the point X. So since X is on L prime, I didn't label this L prime. So X is right here, it's on L prime. It must be the image of some point S on L. So I need to move this. The point S on L. Under the rotation about some point C. So if this is C. Okay, since rotation C 180 degrees is a rotation, S and X must be the endpoints of a diameter of a circle. So what they're saying is, if I rotate S 180 degrees and end up on X, actually this C would have to be a midpoint, so it'd have to be somewhere around here. Okay. All right, so rotate S 180 degrees, it would land on X here. What they're saying is, if you rotate that 180 degrees and S lands on X, then in particular line SX must contain C. So what we're saying here now is, if I draw a line now, let's make this one purple, like so. I'll fix this in a moment. I need to rotate it a little. Okay, so let me go back again. It must be the image of some point S on L under a rotation of 180 degrees, and for example, or meaning the rotation about C 180 degrees of S would be X, must contain C. So C is right here. Since S is a point on L, the red line, and X is a different point on L, it was the intersection of both lines. We have L equals SX. So what they're saying is, if S is on the same line as the rotated X and they go through that center C, they must be a diameter of that circle, is what they're saying. So if I drew a circle now, centered at C, going through X and S, like so, then that would have to be a diameter. And if the point S and X are on the same line, they'd have to be the diameter of the circle, is what they're saying. We have that L equals SX. So the only way for that to happen would be the same line sitting on top of each other. Okay, they coincide. But SX also contains C, which means that L contains C. So if SX contains C, L would have to contain C. Okay, and C was constructed so that it was not on L, so we just contradicted ourselves. That's basically what this paragraph just said. Going through everything we just said, we're now stating that C has to be on L, and it obviously is not. So example 4 says, the construction and claim together implies the following theorem. Given a line L, the red line, and a point P not on the line, then there exists L prime that contains P and it's parallel to L. So let's just say this was P right here. This is a theorem we have justified before using compasses and straight edges constructions, but now we see it follows directly from basic rigid motion in our geometry assumptions. And that's how theorems are born. You try to prove something, and then you disprove something, and therefore a theorem exists that states that these two things have to occur. Okay, page 4 brings us to example 5. We're now ready to prove the first part of the basic fact above. We have two lines, L and L prime. And all we know is that a transversal, AP, intersects both of them, such that a pair of alternate interior angles are equal in measure. Okay, so what they're saying there is this angle here and this angle here are equal in measure because they're alternate interior angles. In the picture below, we are assuming the measure of angle QPA is equal to the measure of angle BAP. Okay, so now it says let C be the midpoint of AP. So they're talking in segment AP. So if it says let C be the midpoint, so let me put a point here. and we call it C. What happens if you rotate 180 degrees around the center C? Is there enough information to show that a rotation centered at C 180 degrees of line L equals the line L prime? A. What is the image of the segment AP? Well, if I rotate a segment 180 degrees, it just lands on top of itself, and if C is the midpoint, then AC is congruent to PC. So therefore, if I rotate a point A 180 degrees about C from line AP, I would end up as P. So what is the image of the segment AP? It is the segment PA. In particular, what is the image of point A? So if I take this point A that is on AP, rotate it 180 degrees, okay? And actually I went the wrong way, that's counterclockwise, or that's clockwise. Rotations are counterclockwise. So rotate this 180 degrees would go this way to P, so the point A would become P. So the image of A is P. Why are the points Q and a rotation of around C 180 degrees of B on the same side of line AP? So in other words, what they're saying is Q's over here and rotating B 180 degrees, put it on the same side of that line AP. Okay, this is lengthy. It says sketch of the answer. The rotation by 180 degrees maps line AP to itself because line AP contains the center C. In particular, it can be shown that the rotation maps one half of plane AP to the other half plane and vice versa. Since Q and B are in opposite half planes by definition of alternate interior angles, and B and the rotation around C of B 180 degrees are in opposite half planes, Q and the rotation centered at C of 180 degrees of B must be in the same half plane. All right. D says, what is the image of R rotated around C 180 degrees of angle BAP? Well, B will become Q, A will become P, so you'd say BAP, and P would become A, so that would end up being angle QPA. So it says, what is the image? Is it angle QPA? And explain why. And the answer is yes, it is. It is angle QPA because under the rotation, the vertex of angle BAP, let me do this, I'll write this as I say it. The vertex, let me get the pen, there we go. All right, the vertex of angle BAP, which is A, right here, this is the vertex of angle BAP right here, maps to the vertex of angle QPA. So basically they're saying point A maps to point P. Ray AP maps to ray PA, and the point B goes to the same point as Q. Since the measure of angle BAP equals the measure of angle QPA, by assumption, ray AB, that's this one, must map to ray PQ. Thus, angle BAP maps to angle QPA. Part E says, why is a rotation centered at C 180 degrees of point of line L equal to line L prime? So why is that the case? Well, since ray AB, so let me just draw this. Here's ray AB right here. Since ray AB maps to PQ, so in other words, if I rotated AB 180 degrees, it would become this, rotated 180 degrees. So it says, since ray AB maps to ray PQ, a rotation centered at 180 degrees of line L equals a rotation centered at 180 degrees of line AB, which equals line PQ, which equals L prime. Okay, page 5 says, we have just proven that a rotation by 180 degrees takes a line L to a line L prime. By the claim in example 3, line L and L prime must be parallel, which is summarized below in a theorem that says, suppose a transversal intersects a pair of lines. If a pair of alternate interior angles are equal in measure, then the pair of lines are parallel. So in discussion it says in example 5, suppose we had used a different rotation to construct the line parallel to L that contains P. Such constructions are certainly plentiful. For example, for every other point D on L, we can find the midpoint of a segment PD and use the construction in example 2 to construct a different 180-degree rotation around a different center such that the image of the line L is a parallel line through the point P. Are any of these parallel lines through P different, in other words? Can we draw a line other than the line L prime through P that never meets line L? The answer may surprise you. It stumped mathematicians and physicists for centuries. In nature, the answer is that it is sometimes possible and sometimes not. This is because there are places in the universe, near massive stars, for example, where the modern geometry of space is not plane-like or flat, but is actually quite curved. To rule out these other types of strange but beautiful geometries, we must assume that the answer to the previous question is only one line. Did you ever think you would say geometry was beautiful? That choice becomes one of our geometry assumptions, parallel postulate. Through a given external point, there is, at most, one line parallel to a given line. In other words, we assume that for any point P in the plane, not lying on line L, every line in the plane that contains P intersects L except at most one line, the one we call parallel to L. Okay, pretty deep stuff. Example 6, we can use the parallel postulate to prove the second part of the basic fact. The theorem states, suppose a transversal intersects a pair of lines, as indicated in this diagram. AP is the transversal intersecting line L and L prime. If the pair of lines are parallel, then the pair of alternate interior angles are equal in measure. Suppose that a transversal AP intersects line L at A and line L prime at P. Pick and label another point B on L and choose a point Q on L prime on the opposite side of line AP as B. The picture might look like the figure below. So they've done that for us. Here's B, here's Q on the other line on the other side of line AP. Let C be the midpoint of AP. So then you'd put C here. Alright, so let's just say, I'm just guesstimating, that's the midpoint right here. Oops. Ay caramba. Right here, and that's C. Okay, let C be the midpoint of AP. And apply a rotation by 180 degrees about that center C. As in previous discussions, the image of L is the line R, is the line rotated around C 180 degrees of L, which is parallel to L and contains point P. Since L prime and a rotation around C 180 degrees of L are both parallel to L and contain P, by the parallel postulate, they must be the same line. So in other words, you cannot rotate L around C and have P on the rotation L prime unless the lines are parallel. Or if you rotate it, it's parallel, it has to go through P. That is the only location. It cannot be closer, it cannot be further, is what this is saying. So rotation is centered at C of 180 degrees, line L equals L prime. In particular, rotating the angle around C 180 degrees of angle BAP equals the angle QPA. Since rotations preserve angle measures, the angles are equal, which is what we needed to show. Okay, page 6 brings us to this discussion. It is important to point out that, although we only proved the alternate interior angles theorem, the same sort of proofs can be done in the exact same way to prove corresponding angles theorem and the interior angles theorem. Thus, all of the proofs we have done so far in class in the problem sets that use these facts are really based in part on our assumptions about rigid motions. Example 7 says we end this lesson with a theorem that we just state, but can be easily proved using the parallel postulate. Theorem: if three distinct lines, L1, L2, and L3 in the plane have a property that L1 is parallel to L2 and L2 is parallel to L3, then L1 is parallel to L3. In proofs, this can be written as, if two lines are parallel to the same line, they're parallel to each other. So if this is line L1, whoops, I didn't choose my line. That was pretty straight until the end. Okay, so if this is L1, okay, like so, and let me label it L1, and then I draw a parallel line to that. So in order to do that, to make sure it's parallel, is I'm going to copy and paste it, and then I bring this line down here and change its color. How about I just do this? Okay, and then copy it again and change its color to orange. Okay, so there's three lines. This is L2 and then L3. So what they're saying is, if L1 is parallel to L2 and L2 is parallel to L3, then L3 is parallel to L1. Okay, so relevant vocabulary for this section are parallel, transversal, alternate interior angles, and corresponding angles. Review the relevant vocabulary, learn it, understand it, love it, and your geometry will be much easier for you. Okay, page 7 brings us to the end of lesson 18. Go to your problem set.